theory of rings, as we have defined, as we have already studied theory of groups, right, which deals with a set equipped with just only one binary operation, only one binary operation. Okay, now our aim is to define on a set with two binary operations, and conventionally we shall denote the one operation by plus, which will be called addition, and the second one will be called multiplication. Just keeping in mind the previous kind of knowledge of integers and real numbers, in which we have add two integers or two real numbers, we have multiplied two real numbers to integers, right? So keeping these names to the general cases, we just denote plus as addition and dot as multiplication, and that will be defined on a set. Okay, so we consider two operations, okay. So one is called addition and another one is called multiplication on a set R. Okay, we just denote this set as R. Okay, now what shall I do with these two operations that has been defined on R? So this will form a ring. Okay, this R will be called a ring equipped with two operations. One is called addition, another one is called multiplication, denoted by plus and dot. Okay, then this set will form a ring if it satisfies the following. Number one is, with respect to addition, the R has to be an abelian group, right? Okay, so with respect to addition, this R has to be an abelian group. Secondly, with respect to multiplication, we require only the associativity. Okay, so R dot will be a semigroup. Okay, we all know that a set equipped with a binary operation is called a semigroup if associativity holds with respect to the operation. Okay, so that means with respect to multiplication, we just introduce only associativity on this set. Okay, and the third one is that since we have two operations plus and dot, so they must have some relations, and which is called distributive laws. Okay, what are those? Distributive laws means, suppose you take three elements for all a comma b comma c belongs to R. Okay. Now firstly you take a dot b plus c. Then this will be a dot b plus a dot c. This is the left distributive law. And secondly,
Sir, what is semigroup mane?
semigroup means a set equipped with a operation, binary operation, in which associativity holds. Associativity.
A b সমান b ওটা হোল্ড করতে পারে a প্লাস b সমান b প্লাস a না a b সমান b a
না, only
ওটা তো
associativity.
কমিউটেটিভ, ওটা তো কমিউটেটিভ।
ওটা commutative. ওটা তোমার
শুধু
এখানে হোল্ড
অ্যাসোসিয়েটিভ
করবে,
বলে
ওটা এখানে হোল্ড
শুধু
করবে,
অ্যাসোসিয়েটিভ শুধু অ্যাসোসিয়েটিভ বলে সেমিগ্রুপ।
শুধু অ্যাসোসিয়েটিভ।
আচ্ছা ঠিক আছে।
মানে আমরা এখন পর্যন্ত রিং বলতে যেটাকে বুঝবো যে with respect to addition it will be an abelian group and with respect to multiplication it has to be a semi group at least. ঠিক আছে? এবার যেহেতু দুটো অপারেশন আছে so they must have some relations, তাদের মধ্যে একটা রিলেশন থাকা উচিত। ঠিক আছে, সেটা হচ্ছে এইটা ডিস্ট্রিবিউটিভ ল, a dot b plus c will be a dot b plus a dot c and a plus b dot c must be a dot c plus b dot c.
স্যার বলছি যে এখানে আটটা কি মানে রিয়েল নাম্বার বোঝাচ্ছে?
না না না, আর তো সেট,
আট থেকে রিং স্যার,
এখানে বলেছি
ওই
ও
রিংটা
আচ্ছা
যেটা
আচ্ছা
রিং।
রিং এর
ও
মডেল
আচ্ছা
হচ্ছে আমাদের কাছে, হ্যাঁ। সো মডেল অফ রিং, প্রত্যেকটা সাবজেক্টের একটা মডেল থাকে। সো মডেল অফ রিং, it is the set of all integers equipped with the usual addition and usual multiplication. ওকে, এটা হচ্ছে আমাদের রিং এর মডেল আর কি, জেড। ওকে, বেশ। So therefore R forms a ring if it satisfies 1, 2 and 3. Okay. For example, the immediate example is z plus dot. Okay. This is a very interesting ring and we shall encounter many properties in z plus dot that will be extended to any general ring. Okay. মানে তুমি জেডে যে সমস্ত প্রপার্টিগুলো দেখবে সেগুলো কি আমরা একটা জেনারেল রিংয়ে কী করে ডিফাইন করতে পারি তার আইডিয়াটা আমাদের কাছে ক্লিয়ার হয়ে যাবে। ওকে, নাও এ রিং, নাও সাপোজ দ্যাট আর বি এ রিং। ওকে, আর ওকে, সো উই ডিনোট a ring by the triplet R plus dot in general. Okay, R is a set and where plus and dot has been defined, which will satisfy this 1, 2 and 3. Okay, now suppose that R plus dot be a ring. Okay, now if you can find out if there exists an element denoted by, that element will be denoted by usually 1. Okay, which has a resemblance with the 1 of z, but these are not equal. This one is the, we denote the element 1 for the property that there exists an element denoted by 1 such that for all a belongs to R, a dot 1, 1 dot a must be a. Okay, that means this 1 is the multiplicative identity. Okay, now in a ring if you can find out such an element, then this is called this 1 is called the multiplicative. This is the multiplicative identity and this is called unity. Okay, this identity will be called unity in the ring. Okay, sometimes it will be denoted by 1 or sometimes it will be denoted by 1r if we put trace on the ring. Okay, whenever it is necessary you can put 1r. Okay, so this is called the multiplicative. This is the multiplicative identity, so this is called the unity in R. And then R will be called, then if 1 exists, then R is called a ring with unity. Okay, with unity 1. Then the ring is called the ring with unity 1. Okay. Okay. Don't mess up this 1 with the 1 of integer. Okay. These are not same, but we denote the unity, this multiplicative identity, by 1, keeping in mind this model. Okay, Z. Okay. Okay. Now, if in addition, suppose you have a ring, again in a ring R plus dot, if you can prove that if for all a comma b belongs to R, a dot b equals to b dot a, then that ring will be called a commutative ring. Okay, if commutativity holds with respect to multiplication, then the ring will be called a commutative ring. Okay, now with respect to plus, we do not need to check the commutative, because we have already assumed that the set, it will form a ring if the first condition is that there has to be an abelian group. So with respect to plus, it is already an abelian group, but with respect to dot, we need to check whether the commutativity holds or not. Okay, and if holds, then the ring will be called a commutative ring. Okay, so your first example is that Z plus dot, right? This is the model of ring, basic model of ring. Okay, so this is Z plus dot, and you will find that the integer 1 will be the unity, right? Unity in Z plus dot, right? And also commutativity holds. In Z plus dot. Okay, so therefore this ring is called, so this is a commutative ring. This is an example of a commutative ring with unity, right? This is your unity. The integer 1 is the unity of this ring. Okay, so this is a commutative ring with unity. Now, number 2, you can find out a commutative ring without having unity, which is that suppose you take 2z, the set of all even integers, then with respect to the same usual addition and usual multiplication that has been defined on Z. If you induce those operations on 2Z, then this 2Z will form a, you can check that this will form a commutative ring with respect to usual addition and multiplication, but it doesn't have unity, right? পাবে 2Z এ কোনো ইউনিটি পাবে? 2Z এ
স্যার হবে না স্যার এটাই
কোনো ইউনিটি নেই। So this is a commutative ring, but
জেড এর সাপেক্ষে হবে।
হ্যাঁ, উইদাউট হ্যাভিং ইউনিটি। ঠিক আছে,
হুম।
তাহলে এটা একটা এক্সাম্পল তুমি পেলে। এরকম তুমি দেখতে পারো আরও এক্সাম্পল যে তারা কমোটেটিভ রিং ফর্ম করছে কিনা যেখানে ইউনিটি নেই। এমন একটা এক্সাম্পল দেখবো আমরা যে ইউনিটি আছে বাট ওটা কমোটেটিভ নয়। ঠিক আছে, সেই এক্সাম্পলটা আমরা করবো, আস্তে আস্তে করবো। ঠিক আছে, আর কি এক্সাম্পল আমরা করতে পারি? যে ধরো সাপোজ you take this set which will be denoted by Z, third bracket I. I is the complex number I. That is the solution of the equation x square plus 1 equal to 0 in the set of all complex numbers. Okay, so we consider those complex numbers whose real and imaginary parts are integers, that is a plus ib, where a and b are taken from Z. Okay, and I square equal to minus 1. Okay, then with respect to usual addition and multiplication, this you can you should check that Zi forms a commutative ring with unity, which is the integer 1, because 1 can be written as 1 plus 0i, right? So this will form a commutative ring with unity 1, and this ring has a special name due to Gauss. It is called Gaussian integers. The ring of Gaussian integers. Okay, so in a similar way you can just take, instead of integers you can take rationals also. So if you define qi instead of zi, that is we consider those complex numbers whose real and imaginary parts are rationals. Okay, so in a similar way you can check that this will form a commutative ring with unity. With unity 1, and this ring will be named as the ring of Gaussian numbers. Okay, this is a ring of Gaussian numbers. Okay, and along this line you can immediately define, you can have this C, and with respect to usual plus and dot it forms a ring, it forms a commutative ring with unity, which is the 1, integer 1. Okay, and not only that, you will find that this C plus dot has some extra property in addition to ring. Okay, so this will be a field because we can check that every non-zero complex numbers has multiplicative inverse also, right? Okay, yeah. Now note that suppose you take any z for z not equal to 0 in C. You take a non-zero complex number, then you can define suppose you take any complex number, okay, see z bar will be defined as the conjugate of z, right? For z belongs to C, where z can be written as x plus iy, then the conjugate is x minus iy, and you can define the modulus also, which is root over of x square plus y square, right? And using these two functions you can immediately have, so you can multiply z with z bar and you will get that x square plus y square, right? In a similar way, since it is a commutative ring, so z bar dot z is also same as that of z dot z bar, and this x square plus y square is actually, so it is mod z square. Okay, now for z not equal to 0, if you consider non-zero complex numbers, then you can immediately have, so z dot z bar by mod z square equals to z bar by mod z square dot z must be 1. So that means for every non-zero z you can have multiplicative inverse. So what is the inverse of z? Z bar by mod z square. Okay, so every non-zero complex number has multiplicative inverse. Okay, okay, so in addition to be a ring, this C plus dot will be having some extra property that makes it more special to the other ones. Okay, and these such rings will be called a field, in which every non-zero element has a multiplicative inverse. Okay, so what will be the so firstly we can define, so suppose you take, so let capital R plus dot be a ring with unity, because without unity you cannot talk about multiplicative inverses, right? So let R plus dot be a ring with unity 1, then R will be defined to be a skew field. Okay, a skew field, we didn't assume the commutativity here. Okay, we just take a ring with unity 1 to talk of multiplicative inverses. So then R is defined to be a skew field, or it has some other name, that is a division ring. Okay, two names having same property. Okay, so ring with unity, then R is defined to be a skew field or a division ring if every non-zero element in R has a multiplicative inverse. Okay. In R. So then this ring is called a skew field. Okay. Now if you add commutativity with this one, then this will be called a field. Okay. So in addition to this, that is a commutative skew field. A commutative skew field is called a field. Okay. And the immediate example that you have already encountered, which is C plus dot, and there are you can also have, for example, R plus dot. Okay. And if you can consider rationals, then it is also a field, Q plus dot, R plus dot, and C plus dot. These are fields. Okay. These are fields. Okay. Now, okay. Now let us have a let us ask a question here. That the question is that, can you define a non-commutative skew field? That is a question that you should have a non-commutative skew field, right? Because if it doesn't have, you cannot tell, you cannot talk about non-commutative skew fields. You should have an example of non-commutative skew fields, right? So what is that? The example is that, a very interesting example that has been introduced by Hamilton. So the example is that, suppose you take